Masses and an inclined plane. A block of mass 2m, up here, is released from rest at the top of a frictionless inclined plane that is permanently affixed to the table. That means the plane is not moving, it's tied down. The block reaches the bottom of the inclined plane, collides elastically with the block of mass m. The top of the inclined plane is a vertical distance little h above the table, and the table is a vertical distance big H above the floor. First of all, find the velocity of block 2m at the bottom of the inclined plane. Then determine the velocity of block 2m after the collision. Determine the velocity of block m after the collision. So you can imagine them going off like this in a projectile motion fashion. Find the horizontal distance traveled by block 2m, and then find the horizontal distance traveled by block m after the collision. Find the velocity of block 2m at the bottom of the inclined plane. So we're going to consider this as our zero reference point for the gravitational potential energy. So we'll say at the top, all you have is gravitational potential energy, and right here, all you have is kinetic energy. That's represented right here. So we have a mass of 2m, a height of little h. That's going to equal 1/2 mv squared, where once again m is 2m, don't forget that. And you'll find that the velocity of block 2m right over here will be the square root of 2gh. Determine the velocity of block 2m after the collision. Well, we have an elastic collision here, but it doesn't fit the special cases. The special cases involve the two masses here would have to be either the same, or one would have to be very much greater than the other, or very much smaller than the other. In this case, it's only twice greater than that. That's not big enough to use those special cases. However, this guy right here, the relative velocity equation can be very powerful. It doesn't depend on the mass, and it will enable us to find the post-collision velocity of mass m in terms of the initial and final velocity of mass 2m. And then we'll use the conservation of momentum to finish the solution. So just stay with me here. You'll see it on the next slide. Here's the general form. v1 will be our velocity of mass 2. Let's see, is that how we did it here? Yes, that's right. So v2 is going to be the velocity of mass m. And then it's just equal to the negative of their post-collision velocities. We move the equation around a little bit, and we also note that Vm in the beginning is 0, right? He's just at rest. So we cancel that out, and then we express the final velocity of mass m in terms of the pre- and post-collision velocities of mass 2m. Now we're going to use conservation of momentum. So our initial momentum is all tied up in 2m, the mass of 2m, because this guy's at rest. So 2mv of the 2m mass is equal to 2mv prime of the 2m mass plus mv prime of the 1 mass, the m mass. Too many variables there. However, the previous slide, we found out what the value of v prime m is. So we're going to substitute that in, and then we come up with this equation. We multiply through by m, we combine like terms, and we come down to here, mv2m equals 3mv prime 2m. And again, remember the prime is the velocity after the collision. And we come up with v prime of 2m is v of 2m over 3. Almost there. We found what the velocity of 2m was previously in part A. That's the square root of 2gh. We substitute that in, and then here we go. The velocity after the collision of the 2m mass is the square root of 2gh over 3. Determine the velocity of block m after the collision. Now we're expecting that will be faster than this block because it's lighter, so let's see if that bears out. We're going to start with this guy right here. We found that back in part A. Okay, we express the final velocity of block m, v prime m, in terms of the pre- and post velocities of block 2m. So that's a good equation. And look, we found v of 2m early on. I guess this was part B. Well, whatever, we did that earlier. And here is what we just found for v prime of 2m. So we substitute those two values in, we add them together, and we get 4 radical 2gh over 3, which is faster than the velocity of block 2m. Find the horizontal distance traveled by block 2m after the collision. Once again, we're back into a kinematics area and we're into projectile motion. That's why you can never really forget anything in physics. It just keeps coming back at you. So we've got 2m strikes m and goes like this, and it'll fall in a trajectory like that. As always with this problem, we start in the y direction to find the time, how long it is before it hits the ground. We have our second kinematics equation right here, and our final height will be 0. Our initial height is big H, okay, so that's now coming into play. We have no velocity in the y direction, and our acceleration is negative g, and our time to fall is the square root of 2h over g. And probably what we're going to do next is find the velocity of block m, and that'll be the same time, right, because it's coming from the same height. To find the horizontal distance, second kinematics in the x direction, and we realize that this term cancels out. It's just 0. There's no x acceleration. And we'll set x0 equal to 0. That's our starting point. So it's just going to be v0x times t, which is going to be v prime, the final velocity of mass 2m after the collision, times the time that we just found. Here's the velocity. Here's the time. We combine, cancel, and we get it goes as far as 2 times the square root of little h, big H, divided by 3. Let's look at block M now. The time it takes to fall is exactly the same, starts out at the same height, so we won't repeat that. We have the same equation for the x motion, and it's just going to be v prime of the mass m times the time. Put the values in, and its distance is 4 times as far as the 2m mass, which makes sense because its velocity is 4 times as great as the 2m mass. So everything checks out here.